Right, so very broadly speaking, talk is divided into three sections. I'll talk a little bit about physics motivations to keep it self-contained. And I'll talk about how Calabi-Yaos feature in string theory and why are CCs, or the complete intersection Calabi-Yau manifolds, important. And there will be machine learning interludes in between. So these are the collaborators and consultants that I work with. Kyron Bull is a student. In fact, most of the work done here was done as part of his master's thesis, and he's responsible for implementing all of this. He has recently moved to Leeds from Oxford for his PhD. Vishnu Jajjala, Yang Hui He are familiar. Yarin Gael is a new computer science professor in Oxford, and he's interested in applying machine learning to various different fields. And there's also DJ Krishnamurthy from DeepMind, who is interested in more formal aspects of machine learning. And the work I'm presenting here was done using the Hydra computer cluster. Right. This is the single greatest contribution of machine learning in our line of business. A few years ago, before the Higgs was announced, I got an email which was marked as spam because the subject line read, "The Higgs boson does not exist." So indirectly detecting the Higgs boson before the LHC was quite impressive. Right. String theory is the only known consistent theory of quantum gravity. Waiting for rebuttals. No loop quantum gravity people here. That's great. It postulates.
Your talk will be online.
Sorry?
Your talk will be online.
I see. Okay. Some video editing might be required. I see. So the two main features of string theory is that it postulates extra dimensions of space, and it relies on a fundamental symmetry called supersymmetry that we all know and love. Also importantly, string theory is an organizing principle for mathematics. It ties together various branches of mathematics, and it's the common playground. Right. Now, in most approaches to string model building, string theory, the gauge group of string theory is broken to the gauge group of a grand unified theory. There are some phenomenological reasons for wanting to do this, which in turn is then broken to the standard model gauge group. And this whole business is called string compactification, where the low energy theory is recovered by hiding away the extra dimensions. And this process places severe constraints on the extra dimensions or the extra dimensional space. So what is the Holy Grail? We were talking about this in the discussion session. We touched upon this. So the Holy Grail for a string phenomenologist would be to reproduce the particle content, coupling constants, masses of particles. Wouldn't it be great if one could find the mass of the electron from one of these models? Explain the origin of discrete symmetries of standard model that help explain things that do not happen. Explain or often invoked to explain the long lifetime of the proton, etc. There are other more fiddly challenges. That is to explain fine-tuning, moduli stabilization, supersymmetry breaking, and so on. So I am interested in a very particular sector of string theory called Calabi-Yau compactifications of the heterotic string. And until around 2010, I think there were around 4 string-derived standard models with semi-realistic spectrum. But since then, there have been tens of thousands. So we have a lot of data now. And this is primarily due to some innovative mathematical constructions. You heard from the previous talk that there are these line bundle constructions on Calabi-Yaus. And this also has to do with increased computational prowess. Right. I highlighted discrete symmetries in the previous slide because it is one of my interests. And in superstring theory, discrete symmetries that you invoke or that you want to have in your 4-dimensional theory must be found as isometries of the compactification space. And there are a couple of important discrete symmetry groups that are not that are not really necessary but are often invoked to explain certain things. So for example, to explain the structure of the mismatch of quantum states in flavor changing processes, one often invokes this group delta 27, or I think it was in Patrick's talk where he spoke about delta 54 in the same category of groups. I use the word category loosely here. There's also R symmetry, which is often invoked to explain why the proton is stable in a minimally supersymmetric version of the standard model. And Alon touched upon this, I believe, in his talk a couple of days ago. And again, the origin of such hypothesized symmetries in the 4D theory is not really understood. So it would be nice if one could find these symmetries as isometries of the compactification space. And not a lot of work has been done towards this classification. There's another advantage to computing discrete symmetries of compactification spaces, which is that most known Calabi-Yaos are simply connected. But most quasi-realistic string models are built over quotient manifolds because you really need a non-simply connected manifold to break the gut gauge group to the standard model gauge group. So flux lines around the irreducible parts of the manifold allow this breaking to happen. Right. So quick overview of Calabi-Yau compactifications of the heterotic string. It is one of the most promising approaches for string model building. And the starting point is that the space-time is realized as being factorized as a 4-dimensional space-time times a 6-dimensional space, where if you assume that the 4-dimensional space is maximally symmetric, and you assume that the internal space is Riemannian, we need a theory of gravity, so it has to be Riemannian. If you further demand that you want an irreducible manifold, reducible compactification spaces are difficult to reconcile chiral fermions with, so we want irreducible ones. And in addition, if you demand n equals to 1's supersymmetry in the 4D theory, then owing to a classification of manifolds due to Berger in the 60s, the holonomy of X6 is, or the internal space is then determined to be SU3. But there's no guarantee that such manifolds actually exist. And the Calabi conjecture proved by Yau, this definitely has to be edited, sorry. Yeah. Proved by Yau, showed existence of such manifolds. So we come to the conclusion that X6 is a Calabi-Yau threefold. Right. I think I can skip over this. Everyone knows what a Calabi-Yau manifold is. But what is the modelized space of Calabi-Yau threefolds? So there are only two unspecified Hodge numbers for a Calabi-Yau threefold, H11 and H21. So these are related to the dimensions of the scalar structure moduli and the complex structure moduli, respectively. And there's also the important phenomena of mirror symmetry, where if you swap the scalar structure and the complex structure moduli spaces, you get a mirror manifold. This is what is known as the Hodge diamond, and the Hodge diamond for a Calabi-Yau threefold with SU3 holonomy exactly, and not holonomy contained in SU3, looks like this. And as you can see, there are only two unspecified Hodge numbers, H11 and H21. And the reason I'm mentioning them is because we're interested, like some others here, in learning these Hodge numbers, machine learning these Hodge numbers. Right. So some of you have, well, probably all of you have seen this plot. In the x-axis is the Euler characteristic, which is twice the difference of these two Hodge numbers. And in the y-axis is the sum of these two Hodge numbers. This is a very beautiful plot. It's called the Hodge plot, and it has roughly 500 million data points. And if you see at the bottom, you can't really see anything, but there has been a lot of activity in the past few years or past several years, filling up or populating this portion. So if you zoom in, you see a bunch of manifolds here. The color coding have to do with the timeline of when these manifolds were, or when these points were populated. And we have a catalog of all Calabi-Yau manifolds that we know up until height 24. So very, very, very large. It's being populated. And the interesting thing is, there are a lot of examples where there are manifolds that are neither complete intersection Calabi-Yau manifolds nor appear in the Kreuzer-Skarke list. Sorry?
Are they equations of such manifolds, or are they completely different?
No, there are some examples which are completely different. In fact, this is the one manifold. Its Hodge numbers are 1, 1. And this is, so if you demand a Kähler Calabi-Yau manifold, which is not rigid, then this is the lowest Hodge number you can possibly get. This is Volcker-Braun's manifold, where he took the 24 cell and he quotiented it out by 3 different discrete symmetry groups. And he found a Calabi-Yau threefold.
What did you start with?
A 24 cell. 24 cell. I can show you the reference.
But this is not in Kreuzer-Skarke.
No. This is not definitely not in Kreuzer-Skarke. Yeah. And against Philippe Candelas's wishes, I have put all these rigid manifolds. He doesn't like it because it violates the symmetry of this graph. But this is the truth. Okay. So how does one? So I'm getting towards constructing a class of Calabi-Yau manifolds called complete intersection manifolds. So if you want to construct it as submanifolds of CM, you can't really do it because a connected compact analytic submanifold of CM is a point. So you ought to be looking at, well, it's not true that you ought to be looking at, but one of the other things you could look at is a complex projective space, because all its closed complex submanifolds are also compact. And the theorem states that all such submanifolds can be realized as the zero locus of a finite number of homogeneous polynomials. And all of us have probably seen examples of this nature. The Fermat quintic is probably the most famous example, where you take coordinates in CP4 and you take this degree 5 polynomial, and the zero locus defines the manifold. Right. Generalizing from the quintic, one arrives at the class of complete intersection Calabi-Yau manifolds, where your ambient space is a product of complex projective spaces, and you come up with a set of k polynomials which are representative of these k columns here. And these guys, Qij's, are the multi-degrees of the polynomials in the various projective spaces. Right. For this to represent a Calabi-Yau manifold, so you can't just write any matrix of integers like this and expect a Calabi-Yau manifold, but if you impose a couple of conditions, you'll be guaranteed to end up with a Calabi-Yau threefold or a fourfold. And so this condition, which says that n1 plus 1 will be the sum of the first row, is essentially saying that the first term class is 0. And if you want a threefold, then you want the number of polynomials and the number of projective factors to have a relationship. Not sure if I've written that correctly, but that's not really very important, so I'll ignore that. In total, there are roughly 8,000 CC matrices in the list, and although this list has been around for a while, we know that only, well, at least 2,590 are known to be distinct as classical manifolds. So actually, it's not really known if the rest, there are equivalences. And there are only 266 distinct Hodge pairs. And the H1 ones range between 0 and 19, and the H2 ones range between 0 and 101. So if I were given a choice to machine learn one of these Hodge numbers, I would probably go with the one which doesn't have so much range. So I'll probably go with H11. Right. The Euler characteristics are all negative for these manifolds, and the largest value is the smallest value is minus 200. Right. And if you compare this with the number of CC fourfold configurations, there are a lot more, and there are four. Sorry, there are four Hodge numbers, but they are independent Hodge numbers, but they are related by this relationship. This is just for reference. We'll not be talking about Calabi or fourfolds, right? Here are some nice pictures. So the matrices and the pictures or the graphs are equivalent. Yes, so the blue things represent the polynomials, and the red annuli represent the spaces, and the degree of connection is given by the number of the multi-degree, and they are completely equivalent. And in fact, this is a bipartite graph representation of this matrix, and I put this here because I think there are applications of this representation in understanding features of CCs using graph neural networks. No one has tried it, but it would be interesting to try. And the other reason for these two particular choices of manifolds is to demonstrate that sometimes the entire second cohomology of the Calabi-Yau descends from that of the ambient space, which is demonstrated by the fact that there are 5 P1 factors here, and the H11 of this manifold, which is the first entry here, is 5. And sometimes it is not. Sometimes, naively one would expect that the H11 of this manifold is 2, but it's in fact 12, because this is actually a CC which is realized as a hypersurface in a product of 2 del Pezzos of degree 4. And so dp4 is p2 blown up in 5 points, so each dp4 factor gives you 6, explaining why the H11 of this manifold is 12. Okay, right. So favorability of CCs is one of the machine learning, one of the properties of CCs that we would like to machine learn. And I've already explained what favorability is, but they are really important because it helps tremendously when you are constructing line bundle sum models, for example, or monad bundles, to have a favorable CC, to have the second cohomology descend from the ambient space. And the fraction of CCs that are favorable is it's 62%, so it's a more or less balanced data set. I think in early this year or probably last year, Lara Anderson, James Gray were able to show that all these CCs can actually be brought into a favorable configuration, sort of like the same manifold, but represented not by this small matrix, but a larger matrix, where you have made it favorable, and they could show that this can be done for all but 48 CC configuration matrices. The rest can be thought of as being favorably embedded in a product of del Pezzo surfaces, which is a nice result. So there are 2 CC lists floating around. One is the old one, and one is the new one. The new one has more favorable CCs. We'll stick with the new one, because the old one requires a bunch of classification projects to really start playing with. Right. So the first question we ask is, can favorability of CCs be learned by machine learning tools? And the 2 tools we use are neural networks and support vector machines. Enough has been said about neural networks here, so I'll skip over this. Instead, I will point out that in our implementation, we have invoked some convolution neural networks, which is very important in the field of computer vision. And there is a visual representation of a CC, which I've borrowed from Yang's first paper on these things. And this is a configuration, CC configuration matrix, it's some random CC configuration matrix, and this is an average one. But truth be told, we have not actually used this visual representation in our as our inputs. This is just for aesthetics for this talk. Right. I will talk a little bit about support vector machines because no one has spoken about it. This is a more geometric approach to machine learning. So if you imagine having two clusters of data, and you are expected to separate them by drawing a straight line, one would imagine that the job is essentially equivalent to finding a hyperplane in this feature space from which all the data points are maximally separated. So it is an optimization problem. In fact, it is a quadratic optimization problem, and there are plenty of solvers that are readily available which one can use. So the issue of being stuck in a local minima does not usually occur in SVMs unless there are special situations. But this is only applicable to linearly separable data. If you have data that where the boundary should really look like a nonlinear curve, what do you do? There's this thing called kernel trick where you map all these data points to a higher dimensional space where the data is actually linearly separable. There you find your optimal hyperplane and you map it back to your original space, and you have this nonlinear boundary, which is great. But in principle, you actually don't have to do anything. What you really need to do is look at the optimization problem that you're solving for the SVM, and there are a lot of inner products happening there, and you replace all the inner products by these kernel functions. And that is enough to have this effect of solving the nonlinear version of this problem. Right. SVMs, support vector machines, can also work as classifiers as well as regressors. So as a regressor, you basically try to fit the flattest line to the data within some allowed residue, epsilon. In the interest of saving time, I'll only talk about architectures if I'm asked, so I'll gloss over it. But the one important point I'll make here is that in our implementation, we have used neural networks and support vector machines, and a genetic algorithm was used to fix the hyperparameters of the neural network, such as number of hidden layers, number of neurons, activation functions, and dropout. Dropout is a way to counter overfitting in neural networks. Yes, so conveniently skipping over that. Okay, these are the results of the first experiment that we have done on machine learning, the favorability. The top curves are the learning curves or the training accuracy curves for the neural net and the support vector machine. And the curves below here are the validation curves. The axis here, x-axis, is the fraction of data used for training. So you see accuracy improving as you train with larger and larger fraction of the data, which is all very nice. And the y-axis is the accuracy, right? And this was a binary classification problem. So we input a CC matrix and we ask the question, is it favorable or is it not? And it's able to do this, with a high degree of accuracy, which is nice. Right. So
what percentage of the CCs are actually favorable?
62.
As you used the old list.
Yes, that's what I made clear in one of the previous slides, that we did use the old list. In the new list, it's very, in the new list, it would be like more than 95%. Yeah, but it would be a nice thing to try.
But 60, so it's only 62% that actually are favorable.
Yeah.
No, it's more, but in the old.
In the list that we are using, that is true. There is an updated list as of.
There's a correct answer. It's either 60% or it's not. If the old list only makes 60% clear, that's not the right answer. The new list casts it in a way that makes favorability obvious, right?
Yes.
And it's
yes.
much higher, right?
Yeah, it is. It's only 48 of 7,890 matrices are not favorable in that sense.
Exactly, so 99% of the examples are favorable. So you could just set, a stupid algorithm would be always yes, and that would have 99% accuracy.
That is true, which is why when we do attack these kind of unbalanced problems, and there is an example of that, we have different benchmarks for that. Yeah. But since we use the old list, because the new list only appeared not so long ago, and many properties of the new list have actually not been computed, so we prefer to stick with the old list.
I'm sorry, so you use the labels of the old list also?
Yeah, of
Oh, I'm
course.
sorry, that's what I misunderstood.
Of course, yeah. Favorability is not a...
Yes, in the old list only happens in 60% of cases.
Yes.
Even though the correct answer is 99%.
Wait a minute, there's no correct answer about favorability.
Either the Calabi is favorable or it's not, I don't get it.
No, it depends on the representation. Depends on the representation. It's not a topological property. It's a function of the representation. Yeah. Otherwise, that would be cheating. Otherwise. Yeah. Great. So the question after this is, can you learn further properties of these manifolds? And we want to learn the Hodge numbers. And these are the list of references where people have computed the Hodge numbers of CCs and CC quotients. And well, this is the first paper here. And as you saw in the previous talk, there's a lot of sequence chasing involved. And but sometimes there are nicer solutions. You do some parameter counting that will enable you to find the H2 one. And I've worked on a couple of these papers here, and it's very nice to be able to compute Hodge numbers for these CC quotients, primarily because sometimes it gives you a very nice insight into understanding the algebraic geometry. And you can be very explicit in your computations. This is one of the graphs that we constructed while trying to understand the Hodge number of a CC quotient embedded in a product of two del Pezzos. And what this graph represents are the intersection properties of the exceptional divisors in those del Pezzo surfaces. Leave it at that. Yeah. So what happens when we try to machine learn H11? So I was trying to motivate earlier why we choose to learn H11 and not H21. It's simply because the spread of H21 is much larger. And in addition, the Euler characteristic that is a function of these two guys is directly computable from the CC matrix itself. So really, there's only one independent thing to be learned here. And we choose to learn H11, right? And here we use a SVM and neural net regressor and a neural net classifier. And these are the validation curves that we get, again, as a function of the fraction of data that we use for training. Yeah, sorry. Yeah.
So the SVM regressor, so just, I mean, 60% are favorable, so 60% of the cases, the answer is just the number of...
Sorry?
60% of the cases are favorable.
Well, we have moved on to learning Hodge numbers now.
Yes. 60% of the classes are favorable, so 60% of the classes, the answer for H11 is just the number of P1s.
Yes, that is true. That would be
true. So the SVM just learns this?
Yes, in those cases, yes, but we do use random cross-validation. So, yeah. But in general, you're right. So 60% cases, it should simply give you the number of P1 factors. Yeah.
And these are the 60% accuracy?
Well, this is more than 60%.
But I guess the point is that the non-trivial cases where it's not just going based on the number of P1s, we know that's regressible.
Exactly, yeah. So these are the accuracies, if this is the measure one is interested in. And the neural net classifier is doing a very good job. It is winning, hands down. And the support vector machine isn't doing as well, as you saw in the validation curves. Okay.
Right. But my question was, have you looked at what the support vector machine does? Does it just give you the number of curves, always? More or less.
Oh, okay. Yeah, that's a good thing to see. I haven't unpacked it yet. I'll find out.
But I guess because it's 70 rather than 60, that could be
That's true, yeah. If it were less than 60, that would be embarrassing. Yeah,
If it were exactly 60.
yeah.
Okay, I mean, it's not so high, but 60, so the question is, does more or less?
More or less.
I'll try to meet the high standards in future experiments. So I'll just keep moving. So this is a nice way of actually looking at, this is a histogram plot of all the Hodge numbers. So from, you go up till 19 here, and the Hodge numbers peak at 7, I think, yeah. So these are all the Hodge numbers for all the CCs, and the green one is the true distribution, and the yellow one is what our machine learning algorithms are predicting. It looks pretty nice. Here we train with 20% of the data, and here we train with 80% of the data, and you see some improvement, right? And this guy looks nice. Right. So this is probably the most important slide of my talk. So the methodology that we have used so far does not really address the fundamental technical issue, and which is that the difficulty of the calculation increases with the number of dimension and the complexity of the manifold. If you have a manifold with a very high H21, you're dealing with a much more difficult beast. And this is one of the reasons why most explicit string-derived standard model computations are on manifolds with Hodge numbers of order 1. Even triangulating polytopes to populate the toric-Calabi-Yau database had to stop at H11 equals to 6. So it would be in our own interest to develop techniques where the training and the data sets are different in character. And one of the nice things to be able to do would be to train with the easy cases and predict the harder ones, for which a paper calculation might be much more intricate, and the answers might actually be unknown. So in that spirit, I'll show you some preliminary results from the paper that we are close to finishing. So we organized the CC data set into a low H11 training set and a high H11 validation set. So we'll train with data where H11 is less than some particular Hodge number, say 1, 2, 3, and so on. And then we'll, oh, man, okay. And we try to predict the high Hodge numbers. So in essence, we are trying to extrapolate, ambitious, but we are also working with a very imbalanced data set. So in essence, you're trying to train a neural network or a support vector machine with a bunch of things. Let's say you have trained it with manifolds up to H11 equals to 2 or 3, and you're expecting it to predict much larger numbers. So until H11 equals to 19. And these are some of the plots from the paper. So this is the SVM predicting H11 for the CC3 folds. Here, if you look at the, well, it looks purple here. I can't tell the color, but this guy is the true distribution. And the blue curve is the curve where we have only fed the neural network, not randomized data from the CC list, but only with data for manifolds with H11 less than or equal to 3. And here it predicts the nature of the distribution correctly. It predicts a peak, albeit at the wrong place. And you would normally expect that as you move up, as you keep on feeding the machine learning tools more and more data with high X's, it should approach the true distribution. But the problem is, when you're doing that, because our training set and our validation sets are complementary, when you go to higher H11s, you are essentially creating another imbalanced data set. So errors are expected to dip and then grow, which is exactly what we find. The neural network actually doesn't do as well. So in fact, when you train it with H11 less than or equal to 3, it mostly predicts anything new you throw at the neural network. It basically predicts that it has Hodge numbers less than 3. So it doesn't do as well. So these are the errors that one can look at. So the green ones are the validation set, as in it's the size of the validation set, and the probably brown, I can't really tell, or gray in my computer. Gray ones are the training sets. So initially you start by training with a very small number of entities, and then you start and train with everything. And because the validation set is complementary, it decreases in size. Okay. So this is what I was mentioning, that the error dips, and then as you train with more and more kinds of data, but eventually the error grows because you have created a very imbalanced problem. And this is the root mean square error for the neural network. The support vector machine, as you saw, is actually doing much better than the neural network at this. So this is quite interesting. So this is one of the main results of our paper. Right. So what is the takeaway from this analysis? That the main takeaway is that these algorithms, it's showing that these algorithms are capable of predicting trends in the distribution from very limited data, which is impressive. And both algorithms seem to predict a lot of values below the limit at which you're training it, which is natural. And the SVM performs much better than the neural net, and in fact achieves a root mean square error of 1 only when being trained with data h11 less than or equal to 7, whereas we can go all the way up to 19. Right. So I'm basically out of time, so instead of struggling with it, I'll show you the highlights. Oh, actually, that's not too bad. 5 minutes, okay, maybe I'll try. So the third experiment that we have done is to machine learn discrete symmetries, and I'll show you some properties of the data set that already exists, and I'll proceed like that. So the data sets that already exist are, the first one is due to Braun, Candelas, and Davis. Well, Braun actually consolidated the project, and he came up with a very technical group theory, representation theory paper, where he ended up making a statement, or well, he performed a classification of all freely acting symmetries realized on complete intersection Calabi-Yau threefolds. And he found that only 2.5% of all CCs, so a mere 195 of them out of 7,890 actually admit discrete symmetries by a freely acting group. Andre Lucas and I looked at this 2.5% manifolds, and we actually found a result which is physically very interesting, because what we found is if you focused on only those handful of manifolds, around 25% of them have residual discrete symmetries that act trivially on the complex structure modelized space. So you're not really specializing in your complex structure anymore. And of which 30% of all the symmetries that we found were actually R symmetries. We find a bunch of abelian and non-abelian groups, and this is the list of groups that we find. And as I said earlier, R symmetries are quite interesting, phenomenologically speaking, at least to some phenomenologists. Yeah. But so this is a very unbalanced data set. This is a more balanced data set, but the size of this data set is very small. So it's very hard to apply machine learning tools here, whereas here it is an imbalance problem. So we will try it, and let's see what happens.
So these symmetries are found by looking at the linearly realized ones on the ambient space.
Yes, that is true. That is true.
If we did this now with the new list, you could find more?
With the new list? So with the new list, one would have to classify all the discrete symmetries first. So
yeah,
one.
That's what I mean. You could redo this and you would find more?
Yes, I think so. Yeah, definitely think so. So the key factor in obtaining symmetries is, well, they essentially descend from projective general linear groups. And the more factors you have, intuitively, it seems like there will be a lot more possibilities. Yeah. And this was the algorithm we employed in classifying those symmetries, but I can talk about it. I love talking about it. So if someone wants to ask me this question later on, I'd be very happy Okay. So the question we asked is, given a CC configuration, can we predict if the CC admits a freely acting group? A binary classification problem, super unbalanced. And like we discussed early on in the talk, we need different benchmarks, because if you're predicting, if the data set is so imbalanced and if you're predicting one value constantly, then you'll be very accurate, but that will be, well, that won't be very meaningful. So we used this confusion matrix, and we used F values and area under the curves. So the key point is that high F value and high area under curve, good. Low, bad. A typical area under the curve that is better than a random guess is the blue one, and the diagonal one is no better than random guess. And if you are in this region, why are you doing it at all? Okay, so we because it was a very imbalanced data set, we decided to synthetically upsample the minorities, and this technique is called smoting. And smoting 0 means you do nothing. Smoting 100 means you take the minority sample and you make it twice. You create some new synthetic entries, and you can keep going on. But the bottom line is that it didn't really help us much. So the values here for the area under the curves and Fs denote that it's still a problem that we haven't properly tackled. It's very difficult. Thank you. Right. So I'm actually done. The possible directions that one could take is that one could adapt these algorithms or other machine learning algorithms to similar problems in the Crutches-Karker list. And of course, this extends very naturally to CC fourfolds, which is nice. And like Fabian made the point, this would require creating some further data sets. One could also envision constructing these line bundle sums on favorable CCs, now that we have a much larger list of CCs. The takeaway from this talk that I think is important is that we should explore further machine learning techniques to extrapolate even better than the results that I was trying to show from our latest paper, by training only with simple geometries and trying to find out about more complex geometries. And we should keep trying to push the boundaries of our stringy understanding of nature with this new ally that is machine learning. So, thank you.
Thank you, Chandra. Yeah, Ina?